to chapter 20. Yeah. And chapter 20, we started talking about transition metals. And remember, transition metals are found there on the periodic table. Between group number 2 and group number 3. Our transition metals, as we've talked about, have a variable type of charge, except for obviously those 3, zinc, cadmium, and silver, which have a fixed charge. And the reason we're talking about really transition metals is they are really the main component in really what we're talking about mainly in this chapter, which is complex ions. And a complex ion, again, is a metal, and typically that metal is a transition metal. And attached to that metal is a bunch of ligands, like water, for example, and they make what are known as complex ions. Now, some of the things we talked about with some general sort of trends on the periodic table. And again, we talked about Z effective, which is the effective nuclear charge, increases as you go up to the right, decreases as you go down to the left. We talked about atomic size, which decreases as you go up and to the right and increases as you go down to the left. We talked about ionization energy, and that increases as you go up to the right and decreases as you go down to the left. Ionization energy being the energy required to remove an electron. We talked about electron affinity, which is the energy change that occurs when somebody gains an electron, increases as you go up to the right, decreases as you go down to the left. And we threw in there at the very end, I think, electronegativity. My periodic table is way too small for this, just so you know. Electronegativity. Should have made a bigger one. Increases as you go up to the right and decreases as you go down. The overall sort of take-home message we talked about is what we kind of know happens. Again, all those trends basically tell us that our nonmetals are really the ones that like to gain electrons and not really lose electrons. And our metals, which are sort of over in the left-hand side of the periodic table, are typically the ones that like to lose electrons and become cations. And obviously, transition metals being more of metals there is definitely going to be the ones that lose electrons. We also talked about electron configuration, which is important. And as we'll see a little bit later on in this chapter, understanding how many electrons that a transition metal may be left with. More specifically, because the transition metals is the D block, writing our electron configuration for those guys and understanding more so what their electron configuration is when they make ions. And that is typically how we find those metals in a complex ion. They are positively charged. And the reason for that is that makes them electron deficient and makes some pretty good Lewis acids, and they were able to accept the electrons coming in from the ligands as well. A reminder that when we do write electron configuration, thank you, that as the electrons go into the atom, they do fill the S first, but there is a switch that occurs once they sort of start putting electrons into the d orbitals, and the 4s, for example, actually becomes higher than the 3D for that first row transition metals. And what that affects is really when these transition metals basically become ions, they are going to lose those s electrons first, and then if necessary, they will delve into the d orbitals there to remove the rest of the electrons that they may need. Remember that transition metals basically are equal to the group number, and that's sort of like the 1 through 18 numbering, and that's how many valence electrons that they have. And also, unlike sort of representative metals, when they lose electrons, they don't end up at a noble gas configuration, like sort of like aluminum or say sodium or magnesium and stuff like that. This is again really important because that metal in the middle does need to be positively charged and electron deficient. That allows it to work well with those ligands, which are going to basically donate some electrons over there. And that's really what we have, as we'll talk about, with complex ions is really a Lewis acid base type situation that's sort of happening in this scenario. And again, that's the transferring of electrons when we talk about Lewis acid and bases, again, not protons. Any questions on any of that there? All right, so these were all the stuff you're supposed to memorize. I'm just kidding. A couple of the last things here. I don't know if we looked at this one or not, but we'll take a look at it one more time here. This is the first row, transition metals. And what we see here is reducing ability increases as you go upwards. And reducing ability is really as something to be a reducing agent, which means this guy is most likely going to be oxidized and a good reducing agent, while this guy down here will be a reduced situation and a better oxidizing agent. Now you may be saying, isn't this the cell potential here? And isn't the more positive one supposed to be the cathode, or the one that gets reduced? And the answer is, yeah, it is, except that in this situation, these are not SRPs, or standard reduction potentials. These are all written as oxidation reactions. These are like standard oxidation potential that's basically happening here. If we were to turn these all into SRP values like we're familiar with, we would basically be reversing all these reactions. And by reversing all these reactions, the signs of all these guys then would technically change. And now our more positive one does make sense, right? As it is the one that should be our cathode, and the one that should be reduced in this case. And so as we see there, we have our reduction happening again closer towards the right-hand side of that first row versus our oxidation happening on the left-hand side. And that also makes sense if you think about the general trend. Things tend to gain electrons as you go to the right on the periodic table. And that, again, is what's sort of happening as we kind of go to the right in that first row when we look at these. All right, here's in case you need to ID the first row transition metals. This is what they look like. I think we saw those the other day, counted some heads and tails. This would be really great information, but you don't do a general unknown anymore. So, here's some of the different oxidation states that these guys make. And again, +2s, +3s, very common. And different oxidation states does lead to different colors of, say, precipitates when they do make precipitates. Here's Mn, which has a bunch of different oxidation states. And again, some of our other compounds here with copper and nickel. And some of these you saw in some of those qualitative analysis experiments. So with our talk here about transition metals, let's get into really the heart of this chapter, which is about coordination compounds. And coordination compounds is, for all intents purposes, you could think of this as like an ionic compound. And because an ionic compound, as you know, should have a positive guy and a negative guy, in a sense, a cation and an anion, that is essentially what a coordination compound is. It is basically a positive guy and a negative guy. It is made up of really two things. It is made up of a counter ion to balance out the charge, and it's made up of a complex ion. And in certain situations, your counter ion can be positive and your complex ion can be negative. But you could also have a situation where your complex ion can be positive and your counter ion can be negative. So you can have a counter ion that's positive or negative and a complex ion that's positive or negative. They will be opposites of each other. Again, that's the idea of the counter ion, as I mentioned, is basically just to balance out the charge of the complex ion. Typically speaking, coordination compounds have no charge like an ionic compound. So all the positives and negatives need to equal 0, very much like you would do with an ionic compound. A complex ion, as I mentioned before, it typically has a metal cation, which makes it very much electron deficient and a nice Lewis acid, and a bunch of molecules or ions attached to it. And these, again, are what are known as ligands. Ligands, again, are Lewis bases. And a reminder that Lewis bases, as we talked about, is something that will donate. a pair of electrons, while something like this is more like a Lewis acid. It's a little electron deficient, will accept a pair of electrons. Now, in order for something to be a good Lewis base or a ligand, it typically needs to be like a polar molecule. And a lot of times it will need some non-bonding electrons there. And that's what we see here with water. It's got those non-bonding electrons on the oxygen. Nitrogen's got the non-bonding electrons obviously there on the nitrogen. Or something like chloride, right? And the way you become negatively charged typically is you gained electrons, which means you're electron rich, if you will, right? So you got extra electrons to give and makes it also a very good Lewis base. So we have these Lewis acids and Lewis bases kind of coming together to make these complex ions. By the way, the attachment here, for example, is the nitrogen here in each of these cases attaching to the cobalt and the chloride, obviously, here in this particular case. When we do a coordination compound, just like an ionic compound, it is always the positive guy first, followed by the negative. So that is always the order, just like an ionic compound is. And again, that could be, as I mentioned before, it could be your complex ion first or your counter ion, depending on, obviously the charge of your complex ion. Now, when we talk about donor atoms, that is really what relates to our coordination number. And it is, again, the nitrogen here that is attaching to the metal, or the oxygen there and water that's attaching to the metal. And that will give us essentially a coordination number of 1 for every one of those molecules. So something like ammonia here will attach, as we saw in the last sort of picture, just to the metal through the nitrogen only. So what happens, though, is, for example, if you had something like this, which I think we saw maybe a little bit earlier on here in our chapter, and we have this complex ion. This is basically cobalt in the middle, and it is attached basically to those 6 ammonias via the nitrogen there. And again, I'll just kind of do it like this. And the attachment is 1, 2, 3, 4, 5, and 6. This gives us a coordination number of 6 for this complex ion. Once again, sometimes people do kind of think that it is the subscript that's down there, and the answer is in some cases it is, and in other cases it's not. The cases where it is when you have a special type of ligand, which is sometimes referred to as being monodentate, or some books will call it unidentate, basically meaning one. And that particular guy could basically only bind in one place per molecule. And that gives you basically a 1-for-1 in terms of the coordination number. But there are some, for example, ethylenediamine here, that is always abbreviated, by the way, with an EN, usually in most cases. And they also will use that abbreviation both in formulas and names. So they'll kind of use that EN in both places because, frankly, nobody wants to write that every time they have to write that name down. So they just abbreviate it. And that is actually what is referred to as a bidentate. And if I draw it, if I remember a little organicness here, let's see here. Looks something like this, give or take, but pretty much like that. And if we have a metal here, what happens in a case like this for EN is it's actually both of those nitrogens that are going to bind to that metal. So in the case of this one, you basically get like a 2-for-1 on the binding here, or the coordination number. So for every one molecule you have of it, it basically will bind in 2 places. So if you had 2 of these, it looks something like this, maybe. We'll bind there, and we'll bind there. And that would give us a coordination number here of 4 in this case. Again, if you were looking at the formula, it would probably just look something like this. And again, it's not going to match the subscript in this case because this guy is bidentate. So again, you get like a 2-for-1 deal instead of a 1-for-1. Ethylenediamine is the most very common bidentate. So is our good friend oxalate there, is also another bidentate sort of ligand, and oxalate looks something like this. Got a couple of double bonded oxygens there, a couple of single bonded oxygens. Minus, minus. And it's actually these two single bonded oxygens that will bind, again, 2 per 1. Honestly, carbonate as well is another one that sometimes you'll get there. If you drew carbonate, right, you got the double bonded oxygen, 2 single bonded oxygens. Again, the 2 single bonded oxygens is what can do that. So if you have something that's a bidentate, it will affect the coordination number. So for every one of those ligands, you got to kind of count the coordination number 2 for every one. If it's monodentate, it's a 1-to-1. Then there are ones that can do 3 or more, which are sometimes referred to as polydentate. EDTA can do it as 6 per 1 molecule. So it basically just grab onto the metal pretty strongly there. There's ethylendyl triamine, which looks just like this guy, except it has 1 more nitrogen. And it can do it in 3 places as well. So you would have to adjust, again, the coordination number. It will not always match sort of the subscript unless they're all monodentate. Then it will match, basically, if you have that. Any questions on that there? So how many of these ligands do we get? It does really depend sort of on the charge of the metal that's in the middle. Because you could kind of look at this like a Lewis acid type situation. We have something that's like a +1 charge. Most likely we're going to get maybe 2 sort of ligands attached, occasionally 4. If we kind of increase the positive charge, making it more electron deficient, we will have a little bit more room, if you want to think about it, for a few extra ligands, 4s and 6s. +3 is most likely going to be 6s, except for gold, which will basically do 4. So again, the idea here is the more and more sort of electron deficient you make the metal, or the metal is, the more willing it's going to be and acceptable it's going to be able to accept those electrons from the ligands that are basically coming in. Obviously, it has basically room to do that. As we know, the positive charge is related to how many electrons it is lost. So if it has a higher positive charge, it's lost more electrons, has now more room for incoming electrons that want to bind to it. And it also makes it more positive, and that negative positive attraction will come together as well. There again, I drew it right, so that's good. So that is ethylendyl diamine, and this is EDTA as you draw it there. That'll be the extra credit, Chris, and draw it. No, I'm just kidding. But it will bind in 1, 2, 3, 4, 5, and 6 different places per 1 molecule. And these are sometimes referred to as chelating agents, which basically means they just grab up the metal. You look on a lot of ingredients on all kinds of stuff, you'll sometimes see something EDTA. And again, it's used there to kind of grab out metals that they don't really want to be part of whatever they're making. Here's a table similar to the one you have in your book of some of these different ligands. Again, all of our kind of polar guys that have some non-bonding electrons are going to be examples of monodentate or unidentate. Our halogens with negative charges, they're going to be also monodentate. Again, our oxalate, our ethylendyl diamine. Here's our diene, as I was mentioning before. It's got 1, 2, and 3 nitrogens where it can attach. And there's our ethylendyl aminotetraacetic acid, or acetate, is our guy there. By the way, it's got kind of a negative charge, negative charge, negative charge, negative charge, kind of -4 charge overall. But that really can grab a metal pretty well. So what we're going to be looking at now are these coordination compounds, and this is typically how it's written. And by the way, the complex ion is typically written in the brackets. So the thing in the brackets typically are the complex ion part. The other part would be the counter ion. So why don't you take a moment here, and for each of these sort of complex ion part, identify the oxidation number of each of the metals, the transition metals there in the complex ion. So take a moment and see what you come up with. Okay, so let's take a look at it. So once again, in the brackets here is going to be my complex ion. That would make, by the way, my potassium the counter ion. So here we're just going to kind of assign it like normal. So OH is hydroxide, which hopefully you know is -1. There are 4 of them, which gives you a -4. We do have 1 potassium ion on the outside, which should be +1 since it's group number 1. That means here our gold is rolling with a +3 oxidation state in this case. Any questions on that one? Coming to the guy on the right, this right here going to be our complex ion. This again would be our counter ion in this case. So starting with NH3, NH3 is neutral, so nothing. That's NO3, which is NO3 minus. That is nitrate, which is -1. And there are 3 of them, which gives you a -3. Again, much like an ionic compound, coordination compounds typically should equal 0, which means to make that equal to 0, we would need also a +3 here for our chromium. First off, any questions on that there? Now, if we wanted to know the coordination number here for the first one, the coordination number here would be, it would be 4, as it's basically a gold metal that has 4 hydroxides attached to it, attached through the oxygens in each of the hydroxides. So 4 hydroxides, 4 oxygens, coordination number here would be 4. Coordination number for a guy here on the right is going to be 6 in this case. Same idea. Basically, we have a chromium in the middle. We have 6 ammonias attached to it, and each ammonia will attach to the nitrogen. So that gives us 6 nitrogens that are directly attached to it and gives us a coordination number there of 6. Any questions on how to get to that there? Now, if we were to just look at our complex ion part here by itself, what would be the charge here of the complex ion by itself? We know again that's -1. That gives us a -4. We figured out the gold here is +3. That means that our actual complex ion in this case is a negative complex ion, and it has a -1 charge. That is also why when we look at the formula for potassium, we just have 1 of them there, because all we need is a +1 to balance out the -1 here to again give us our really neutral coordination compound that looks something like this. Same thing if we go to our guy here on the right. We got this. Again, that is 0. We figured out that the chromium in this case is +3. That means that our complex ion on the right-hand side is actually a positive complex ion. It has a +3 charge. And that is why when we look at our counter ion, which is nitrate, we don't just have 1 of them, but we actually have 3 of them. And that gets us something like this, which gives us a grand total of -1, -2, -3. That balances out the +3 that we have over here. Again, much like an ionic compound, equaling 0. And here, that gets us back, obviously, to the formula that's above there. Any questions on that? So the counter ion is really just used as that to balance out the charge on the complex ion. So as you can see in this example, you can definitely have a complex ion that's negative, which means you will have a positive counter ion that will come first in the formula. You could also have a positive complex ion like the second one there, which means your counter ion will be negative and come second in the formula. Any questions on any of that there? All right, then let's talk about naming. I know you thought naming was done, but let's get a really long piece of paper here and start naming things. So to name these coordination compounds, as I mentioned earlier, it is like an ionic compound. So we're going to go cation before anion. So positive guy before negative, both in name and formula. Within a complex ion, we do the ligands in alphabetical order, regardless of prefix. And what I mean by that is if you had 2 of the same ligands, so you had 2 waters, you would use a prefix like di for 2, kind of like what you do in type 3 naming, where you use like mono, di, tri, and all that kind of stuff, except we don't use mono here. But you would use di, tri, and so forth. And we would not look at the di part of the name. You would look at the first letter of the actual ligand's name to do it alphabetically. Now, some anionic ligands end with the letter O. Neutral ones are usually called by their name. And there are some exceptions. Water is aqua, or depending on your book, people roll with aqua as well. CO is carbonyl, NH3 is amine. Now, when there are several ligands of the same type within that complex ion, like I was just mentioning, we do use prefixes with the names. And again, di meaning obviously 2, tri 3, tetra 4, penta 5, hexa 6. Now, if by some chance your ligand already has one of those prefixes in its name, then we roll with bis, tris, and a little tetrakis, right? So that is 2, 3, and 4. What do I mean by that? I mean by like this guy right here, En. The name of this guy is ethyl endyl diamine is the actual name of the ligand. Since it has the word di in its actual name, if you had 2 of them, you would actually call it bis, ethyl endyl diamine, instead of ethyl endyl diamine. So again, if the ligand itself has some type of prefix in it, you got to roll to the bis, tris, and tetrakis if necessary. Craziness that who made up this stuff. The oxidation number of the metal is always written in Roman numerals and is following the name of the metal. So we always go with ligands attached to the metal first in alphabetical order. The name of the metal will always come, and listen what I'm going to say here, it will always come at the end of the complex ion part of the name. So that doesn't necessarily mean it's always at the end of the name, but it's at the end of the complex ion part of the name, which could come at the beginning or it could come at the end. So that is always there. We do use Roman numerals for everything typically in these guys, even things that we normally do not use Roman numerals for, like silver, which has a fixed positive charge, we use Roman numerals for. Zinc, cadmium, those guys. So we do use Roman numerals for them, even though normally we don't because they may have a fixed positive charge. Also, oddly, it's not really a Roman numeral, but we do go like a 0 in there as well sometimes. You can have a neutral metal, as odd as it sounds, can pop up occasionally. And we do roll with a 0 as well, which obviously is not necessarily a Roman numeral, but we do use a 0. So that's a little bit different. Now, also a little bit different is, as we just saw in the previous examples, your complex ion could be positive or it could be negative. So if your complex ion part of your coordination compound is positive, the good news is you just roll with the regular old metal name, like iron, copper, whatever it may be. If your complex ion is a negative complex ion, you roll with the old school name, like ferrate, plumate, cuprate, arurate, zincate. You put a little ATE at the end of most of those as well. So you kind of roll with the old school type name for the metals if the complex ion is negative. So here are some of those prefixes, not really prefixes, but some of the ligands. So water's aqua, amine, methylamine, carbonyl. Our halogens are kind of named like we do in organic: fluoro, chloro, bromo, iodo, a little hydroxo, a little cyano there for some cyanide. Here's what I was talking about, kind of the older school names here. So iron would be ferrate, copper, cuprate, plumate, argentate, arurate, and stannate, to name some. And again, this is when your complex ion is negatively charged, is when you got to roll with that. If it's positively charged, you roll with the regular name. Yeah, it's like normal. So positive complex ion, regular name, negative complex ion part, kind of old school name rolling out there. Here's a few more sort of ligands and their names. We got bromo, chloral, a little carbonato, a little oxalato. I feel like I'm ordering some coffee. Maybe a little aqua to go in there as well. There is our EDTA. That is a big name right there. And that is our EN that we do use for abbreviation as well. So for example, if we went back and looked at what would we have there? Those previous ones there. So we got this guy here. Okay. Oh, I just got this way. I'll do it here. I got some room. All right, so let's say we wanted to name these guys here. So first off, we kind of did a lot of the work here on these two examples to figure out what we need to do. We already know a couple of things. We know the potassium here is our counter ion. We know this is our complex ion, and we also know that our complex ion in this particular case is negatively charged. The good news on the counter ion is you frankly just use the name of it. It doesn't matter how many you have of them. So if you had more than one or whatever it is, you would just kind of name it like normal. So for example, if we had, say, something like Na2S, right? That would be sodium, right? Sulfide, right? And again, even though there's two of them, it doesn't make a difference. And that's sort of the same idea here with our counter ions. It doesn't make a difference in how you name it. Or how many there are in terms of the name. So we would start with potassium as our first part here. And now we're going to go with our ligands in our complex ion. And we have 4 of them. And again here, if we go with 4, that is tetra. This is hydroxide. So again, if you kind of refer to that table we just saw there, it goes right here. They're just hydroxide right there. We have hydroxo, right, as we come here. So pop that in there. Got a little hydroxo. And now we come to our metal. And our metal here in our complex ion comes from a negatively charged complex ion. So as I mentioned before, this is going to be old school naming here. And we're going to go with gold, right, which is arurate is how we would want to name it. And we will pop that in there. That's going to be arurate. And we do need the Roman numeral, which in this case would be 3. So this would be, it rolls right off your tongue. Potassium tetrahydroxo arurate 3 would be the name of this coordination compound. Now, if we come to our guy on the right here, in this particular case, we did kind of the work here previously, and we saw that our complex ion is positively charged, which means for chromium, we could just call it chromium. We don't have to use any other name. We are going to start with our ligand, which are 6 of those. So that is going to be hexa. This is amine for ammonia. And again, here we're going to use chromium because it's positively charged. We still need the Roman numeral, which is 3. And now we come to our counter ion. So as I mentioned before, even though there are multiples of the counter ion, it doesn't matter in terms of the name. We just use the name of it. In this case, the name is a polyatomic ion name, which is nitrate. And this would be nitrate here. Yeah. So a little hexamine chromium 3 nitrate. Question on that there. Now, by the way, if you just had the complex ion parts, so if you just had the complex ion here, and you were asked, what is the name of that? Well, frankly, it is just this right here. This would be the hexaamine chromium 3. And because it's an ion, you put ion at the end of it. So it's basically the same name. Just take off the counter ion part of it and just put ion at the end. Same thing here. This guy here, just the ion would be, get rid of that and put ion at the end of it here. And that would be how you would name if you had just the ion, just complex ion without the counter ion present. So basically named the same way. Any questions on that there? All right. Fun with naming. This is good times had by all, sort of. All right, so why don't you give this one a go, see what you come up with. What is the name of that one here? We'll do the one that's up on the board, maybe different than what's on your handout. I don't remember. Okay, let's take a look and see. So this right here is my complex ion part. That would make the potassium my counter ion. We'll do a little housekeeping here, see what's going on. We got oxalate, which is -2, and there's 3 of them. That gives us a -6. Potassium is +1, and there's 3 of them, gives you a +3. +3 -6 is -3. That means my chromium here is going with a +3 charge. My coordination number in this case is, it is 6, as oxalate is bidentate, which means you get a twofer on that deal, right? So again, not always that number on the bottom. It's a 2-for-1 special. That means, by the way, just looking at it, I already know my complex ion is positive or negative. It is negative because it comes second, right? So positive, then negative. So I know it's going to be negative. That means a little old school name there for chromium, which would be some chromate. So here we're going to start with the counter ion. That is potassium. It doesn't matter how many you have, it's just potassium. Now we're going to go here. We got 3 of the oxalates. So that's a little trioxalato. Yeah, sounds good. And we're going to go with a little bit of chromate, Roman numeral 3 in this case. I will say that some people, because it is a bidentate, they will actually go with tris oxalato, chromate, Roman numeral 3. So oxalate's a little bit interesting. Some people will actually go with the tris, or you could do tri in this particular case. So as I was talking about before, when we talk about the metal, always comes at the end, and maybe we should go back and take a look at that one we were just doing there. When we're talking about the metal part coming at the end of the name here, because it's a negative ion, it comes at the end of the name. But here, because the ion was positive, it comes at the end of the complex ion part of the name, not the actual end of the name. So again, that's what I was talking about before. The metal with the Roman numeral should always come at the end of the complex ion part of the name. So if your complex ion is positive, it will not be the last part of the name, but it'll be the last part of the complex ion part of the name. Question on that one there. All right, try a couple more. Here's some more fun element names in case you need. Top one, we want to know what the name is. Bottom one, why don't we write a formula? See how that goes. Okay, let's take a look to see how you're doing. We'll start with the first one here. Want the name. Again, the guy in brackets here, our complex ion. That's going to be our counter there. And we know just from the placement here that our complex ion is actually positively charged because it comes first. That would mean our counter ion is negatively charged because it comes second. Water is 0. Chloride is -1. There's 2 of them, gives you a -2. We also got a -1 for the chloride on the outside as our counter ion. Again, to balance that out to 0 here, our chromium is going to be +3. By the way, the coordination number here is 6 in this case, 4 for the waters and 2 for the chlorides that are attached in this case. Each of the waters attached in one place, and each of the CLs obviously attached in one place as well. So we could go with 2 chlorines there, or chlorides, so that's a dichloral. We also have 4 waters, which is a tetra aqua or aqua, depending on your preference. So we're going to put those together here in alphabetical order. So alphabetically, that is C versus A. A is going to come first. Again, not looking at the prefixes here. So this is going to be tetra aqua or aqua. Dichloral. Now we're at the end of the complex ion part of the name. We will use chromium because it's a positively charged ion. Roman numeral 3. And now we have Cl, which is just named like a normal ion, which is chloride. Again, if you had multiple Cl's at the end there for the counter ion, it would still be called just chloride at the end, even if it was like Cl2 or something like that. Any questions on that there? Now we want to give some formulas. So just gonna really just build the parts. By the way, I know this part right here is my complex ion part because that is a Roman numeral there after a metal. I also know it's positively charged my complex ion because frankly, that's a regular name there for cobalt. And this would be my counter ion in this case. So tris ethyl endylamine means I basically got 3 of those, unless you want to write out the formula, but you can use En3. Cobalt 3 there, I think it says. Yeah, there it is. Cobalt 2. It's kind of like a 3, but not so much. So cobalt with a +2 charge there, again from here. And our sulfate here, which is SO42 minus. So putting our complex ion together, CO, En3. So now we want to think about what is the charge on it. So we know that is +2. This is 0. That means overall here, our complex ion actually has a +2 charge. And that's important because that tells me for sulfate, I actually only need one of those, right? Because that's a -2 charge. And that would give us our proper formula here for our coordination compound. That looks something like this here. Again, the -2 will balance out the +2 that we have there. Any questions on that one there? All right. Try a couple more here, a couple more names. Okay, let's take a look here. Again, we see complex ion first, so it's positive. And again, the chloride here would be our counter. Looking at oxidation state, so 0 for the ammonia, -1 for the chloride there, -1 for guy countering, and -2 overall. So here the cobalt's going to be +3 in this case. Coordination number on this guy will also be 6 in this case. It's not always 6, but it happens to be the last few. I got 5 and 1 going on there. So here we have 1 chloral as a ligand. We have pentamine for our ammonias there. And we have cobalt Roman numeral 3, as we could use the regular name, as it is a positive ion. So putting this together, we are going to go A before C, and again, ignoring the prefix. So this will be a pentamine chloral. Again, we don't use mono here, so we just use chloral. Cobalt 3. And counter ion, even though there's 2 of them, will still be chloride in this case. Yeah. Any questions on that name? Yeah. Technically, we don't usually use mono with this type of naming. So if it's just one, you just kind of use whatever it is and stuff like that. Yeah. Yeah. So the coordination number, if we just look at the complex ion part, which is basically this part here, right? And overall, it basically has a +2 charge. So basically what that has is a cobalt in the middle, and there is 1, 2, 3, 4, and 5 ammonias attached to it. And it also has 1 chloride directly attached to it. So in terms of coordination number, this 1 on each of the ammonias will attach to the nitrogen. So that is how we get to our 6 in this case. Yep. Other questions? Yeah. Yeah, so that's really what it is. It's the definition of coordination number is the number of bonded atoms directly to that metal in the middle of the complex ion. So, and that's why when we get to like a bidentate, because each one will actually bind in 2 places per molecule, you get kind of a 2 for 1 in terms of the coordination number, because there's actually 2 bonded atoms to the metal in each of those ligands. Other questions? All right, taking a look at this one. This is a counter ion, as this guy here is our complex ion. And in this particular case, we're just going to name our counter ion, even though there's multiples, it's just going to be potassium. So that's sort of the deal with the counter ion. Doesn't matter how many you have. If it's a polyatomic ion, just use the name. If it's a negatively charged single guy, you use ID at the end of it. And then obviously, if it's a front guy, it's probably going to be a metal. So just the whole name of the metal. Here, we're looking at what we got going on. That's cyanide, which is -1. That's a -6 overall. We have a +1 for the potassium, and there's 3 of them. Gives you a +3. So +3 -6 means the iron here is going to be +3. Coordination number here also going to be 6, as Cn- is monodentate. And basically, in this case, probably the carbons attaching in each of these cases. Um, so we got hexacyano, right? And for our cyanide, and we got ferrate here as our complex ion is -3. So a little potassium, hexacyano, ferrate 3 here would be our name. Any questions on that one there? All right, last couple here. Let's do a couple more formulas. Good, let's go back. There we go. All right, so the formulas for each of these guys. Okay, so let's take a look. Again, here we can see that this is my complex ion part of the name because my metal comes at the end. Second one, this is actually my complex ion part of the name as the metal comes at the end. So just kind of taking the parts here, triamine means I have basically 3 ammonias. Takes care of that. Got me a bromol, which is a Br minus. And I got a platinum that has a +2 charge in this case. So putting together the complex ion part, a little PT, a little NH3, and a Br. We can now kind of use that to figure out our overall charge of our sort of complex ion. This guy's 0. This obviously is a -1, and that's a +2. That means overall, really, our complex ion is +1. And that's important for our counter ion, which is chloride. That tells us we just need basically 1 chloride there to balance out that +1 charge. Any questions on that one there? Yeah. I would say it's typically speaking, usually they'll go metal first and then ligands in alphabetical order is sort of how it is. Technically, I don't think I would mark it wrong or anything like that, as long as they're all in the box there together. But that's usually kind of how it goes. Yeah. Other questions? All right, so this is obviously our counter. So that's potassium. I know that's a K plus. So hexafluoral, that seems like 6 F's there. And cobaltate is cobalt with a +3 charge. So here I got this sort of happening here. Again, each one of these are -1, and there's 6 of them. So that's a -6, and that's a +3, which means the complex ion part here is actually -3 overall. And again, that's important because I will not need 1, not 2, but I'll actually need 3 of those guys to get to a +3 to balance it out. And we would put that in front as it is positively charged in this case. Any question on that one there? All right, so fun with naming and formulas. Let us continue on then and talk about isomers. And isomers are things that have the same formula, but sometimes different arrangements in 3-dimensional space. And because of that, they do give us different sort of properties in some sense. Isomers can be one of kind of 2 ones, sort of categories, if you will. We could have structural isomers, which have different bonds, and sort of a class of those could be a coordination isomer or a linkage isomer, and we'll talk about what each of these are in just a second. We could also have stereoisomers, which have the same bonds but are arranged in space sort of differently, and that could give us geometric isomers of cis or trans, and also optical isomers as well. So let's talk with coordination isomers. So both of these guys basically have the same elements involved, if you will, all the way around. But the difference here is in one case, the top case, this is our complex ion. And in this case, the sulfate is actually a ligand in this particular case. So that sulfate is attached to the chromium along with the 5 other ammonias. The Br in this case is acting as the counter ion. Now, if we take the guy on the bottom, which again has basically all the same things there, it's got a chromium, it's got 5 NH3s, it's got 1 Br and 1 sulfate. They basically have the same stuff in each of them. In this particular case, though, the bromine, because this is again our complex ion, the bromine in this case is now part of the actual complex ion. So the bromine is attached to the chromium. And in this case, the sulfate is acting as the counter ion. So coordination isomers will basically be the same sort of elements and everybody involved. But in one case, one of those guys will act as the ligand and the other one will be the counter ion. And then they will kind of switch. And the guy that was acting maybe as a counter ion is now going to be an actual ligand and part of the complex ion part of it. Now, different to that is what is known as a linkage isomer. And a linkage isomer is basically the same stuff attached as well. But the difference comes between how the ligand attaches to the metal. So in the case of NO2 minus, you have a nitrogen and you got a couple of oxygens. In the first case here, what we see is the NO2 minus is actually attaching through the nitrogen. So it's using the nitrogen to attach to the metal. But because it also has an oxygen, which has a negatively sort of charge and also some free electrons on it as well, it could also attach via the oxygen. And this is what is referred to again as a linkage isomer. The difference between these two things is how the ligand is attached to the metal. And again, in the first case here is the nitrogen attaching, and the second case is the oxygen attaching. Once again, everything else is sort of the same. Everybody there is the same. It's just the kind of connection that's happening is different in each of those cases, and that's a linkage isomer. Any questions on that there? Now, stereoisomers, also referred to sometimes as geometric isomers, can be cis or trans isomers. And cis and trans basically means a couple of things. Cis means basically same side, and trans means opposite sides. And in organic chemistry, you see that a lot with double bonds. And something on the same side of the double bond is known as cis. Something on the opposite sides of the double bond is known as trans. Now, in this type of situation, we're talking about the same side of like the plane of the molecule, or opposite sides of the plane of the molecule. So some atoms, they have the same atoms, the same bonds, but they have different bond angles. This is common in square planar complexes. Here is square planar. Perhaps you remember that from the expanded octet of geometry there. And it's a symmetrical sort of arrangement. Here we have the PT in the middle, and if you look at the chlorine, they're on the same side here. And you can even look at the ammonia here is also on the same side, basically, of the plane, and that would make it cis. On the bottom here, our groups are on opposite sides, and that is what is known as trans in this case. You could also, if you wanted to, look at the ammonias, which are also on opposite sides of each other. So this is very common, and I guess this is our square planar sort of geometry. We also could see it in this geometry here, which is everybody's favorite octahedral type of steel happening. And here we have in A our trans isomer, and we can look at the chlorines here. It is above and below the plane, basically in the middle, and that's on opposite sides of the plane, and that would be trans. Here it's kind of above and also above here on the same side, and that would be cis in this case. So we see this also in our octahedral sort of geometry as well. So trans opposite, cis the same. They're identical in this case. Just the orientation of certain groups in relationship to each other are different, which gives us cis or trans. If you were to name these, they sometimes will put cis or trans in front of the name to tell you cis or trans that's happening in that case. Now, optical isomers are isomers that have opposite effect on plane polarized light. They are molecules that have non-superimposable mirror images. Those are what are referred to as being chiral compounds. And typically chiral compounds, a lot of them, for example, in organic chemistry and such, have a chiral carbon. And what that usually means is it has 4 different groups attached to it. What's an example of a chiral thing? It's your hand. If you put your hand up to the mirror, you get your other hand staring at it. And if you take your mirror image out, you do as much as you want with it, you'll never be able to superimpose it correctly on your other hand. I could do this, my thumbs are good, but palm up, palm down, not so good. I could flip this way, palms are good, thumbs wrong side. So you could rotate as much as you want. If you pull out the mirror image, it will not be able to superimpose on itself. And that's what's known as a chiral compound, is something that has a mirror image that cannot superimpose. Achiral compounds, as you'll probably learn eventually, is what is known as guys that have mirror images that actually do superimpose on each other. So if you stick it up into a mirror and take the mirror image out, you could rotate it and get it to sit perfectly on top of it. And a chiral compound, even though visually may look like it will do that, as you rotate, what you have to remember is these things are at certain angles, right? So as you rotate, even though it may just visually two-dimensionally look like it's going to sit nice, it's not going to be at the right angle. Something is always sort of off. The isomers are known as enantiomers. Again, plane polarized light. You can measure the angle of deflection as it goes through there. And there's your hands there, sort of mirror images. So if we take a look at this here, we have isomer 1 and isomer 2, and they're mirror images that cannot superimpose. There's no way that 1 can be turned to become 2. So why is that? So if we take our original guy here and put it up into our mirror, what ends up happening when it reflects over, kind of reflects as it does, it actually reflects that this bond in the original guy is actually right here to this guy in front. But in the mirror image, when you take it out, that bond is now transposed to the guy in the back, which means as you start to rotate it, there will always be a bond that's not going to fit correctly and you can't get it to sit there. And that is a chiral compound that the mirror image will not superimpose on each other. Now, if you take a look at these two here, we have identical mirror images here. And here, when this guy gets reflected, we actually maintain the same bonds, basically, from the mirror image to the original. So if you were to pull that out, you could sit that right perfectly on top of the other one. It's going to fit perfectly. Once again, over here on our second guy, the cis, we have that transpose sort of connection that occurs. And again, that is going to be the troublesome here and not going to let that do it. So a lot of times trans guys will be okay. They'll kind of have mirror images that can be superimposed. It's those cis isomers will always get that kind of opposite bond that will kind of occur as it goes into the mirror image. Now, enantiomers are 2 molecules that are mirror images of each other that are non-superimposable. A lot of them are used as biomolecules, and they can be used in drugs where only one of them is effective because they have the different sort of connectivity. They also will have some different properties. So some may have some properties you want and some may not. Any questions on isomers there?